Okay. Can you hear me?
Yes.
Okay, then good morning, everyone. As initial reminder, let me recall that there is this opportunity related to the IEEE iOS Symposium 2022 in Venice. There are few seats available for volunteers, so please let me know as soon as you decide whether joining or not. In your name, I will forward your contacts to the organizer. Yeah, free lunch, free accommodation in Venice, and opportunity to attend a research event. Okay, let's jump back to non-idealities of op-amps. So we have started the discussion of several non-idealities, in particular related to the limited gain of the op-amp. Then we have discussed the effect of the offset. And in the previous class, we have also introduced the problem of having non-infinite input impedance in the input terminals of the op-amp, and therefore currents flowing into the op-amp. So what happens if we have a situation like this? So suppose that the inputs are null. And you have a configuration like this one. So inputs null, either the input being applied at this node or this one, no matter what, but we are considering the input nodes. However, there may be some currents, undesired currents flowing in these branches. Let's call this current I plus and I minus. If indeed these currents are present, the output voltage will not be equal to 0 as desired because the inputs are null. To compute the actual value of the output, we can apply the superposition principle, since all these effects are linear, which means that I can compute the output when as a function of the negative I negative or I minus when I plus is equal to 0, plus the effect of I plus when I minus is equal to 0. So let's consider the first condition. First step, I plus equal to 0. And I want to determine the relationship between I minus and the output. So when I plus is equal to 0, the voltage drop across R3 is null. So this implies that V plus is equal to 0 as well. If in this case we assume that the gain is sufficiently high, then as you may know, there is the virtual short circuit assumption. So we can assume that also V minus is equal to 0. If V minus is equal to, is equal to 0, this means that the voltage drop across R1 is also equal to 0. And this implies that the current through R1 is equal to 0. So this means that the current flowing in R2 is equal to I minus. And this, in turn, implies that V out is equal to the voltage drop across R2. So V out is equal to R2 times I minus. This is V out as a function of I minus when I plus is equal to 0. Okay, so it is this function here. Second condition, to determine F2, we now assume that I minus is equal to 0. I plus now it's not equal to 0 because we have I plus generating a voltage drop across R3. In particular, provided that the orientation of the current I plus is this one, this means that V plus is equal to minus R3 times I plus. Which should be equal also to V minus, because the assumption of the large gain is still valid. Okay, so virtual short circuit in the new condition. So we can compute V out by taking into account that the voltage drop here is minus R3 I plus, and this generates a voltage drop across R1, and this voltage drop generates a current which flows into R2. By skipping the mathematical passages, we can finally find that V out is minus R3 times I plus time R1 plus R2 over R1. Okay, this can be seen also as the effect of the voltage divider between the output and this intermediate step here. Okay, so you can compute the voltage here as V out time R1 over R1 plus R2. Therefore, this quantity here is equal to this one, so you can flip it and get this result. Okay, now we can combine result 1 and result 2 to apply the superposition principle. So basically, V out shall be given by this effect minus R1 plus R2 over R1 multiplied by R3 times I plus this second effect, so R2 times I minus. We can somehow manipulate this expression to highlight the role, better highlight the role of I plus and I minus. So for example, if we keep I plus as R1 plus R2 over R1 times R3 times I plus. And then we act on this term by multiplying this term times R2 times R1 over R2 plus R1 times R2 plus R1 over R2 times R1. And this is globally equal to 1, this effect, of course, times R2 times I minus. So we have added this extra term to the initial one. Why proceeded this way? Well, because basically I want to highlight the fact that in this way we can simplify this term with this one. So we have R1 plus R2 over R1, which multiplies now this term and this one. Another important thing to observe is the fact that R2 times R1 over R2 plus R1 is equal to having R2 in parallel to R1. Sorry. Okay, so now let's rewrite again the initial expression by collecting this term. So R1 plus R2 over R1. Then we have minus R3 times I plus, and then we have plus this term here, which is R2 parallel R1 times I minus. Okay? Well, this is quite interesting because then if I plus is more or less equal to I minus, and we select R3 so that it is equal to R1 parallel R2, then the output voltage due to this undesired effect is equal to 0. Okay, so with the proper selection of this R3, you can get this nice cancellation of non-idealities. This is the reason why I've added this R3, which is quite untypical. Okay, typically we just connect the input to the positive terminal. Okay, or the positive terminal directly to the ground when we are considering a non-inverting, an inverting configuration. So the typical way to sketch this circuit is this one for the inverting configuration, or applying the input here for the non-inverting one. So in some cases, when the input current are different from 0, it can be useful to add this extra resistor here. Okay, because if you select R3 in order to be equal to R1 parallel R2, then the output is null for null inputs, as desired. However, we have to take into account the fact that in many practical situations, we may have I plus slightly different from I minus. Okay, so I plus may be different from I minus. So this quantity here is usually referred to as offset current. If you still keep R3 equal to R1 parallel R2, then you can plug this result here and have the following global result. So the output voltage is equal to 1 plus R2 over R1, that is this part here, time minus R2 parallel R1 time the offset current. Okay? So this is sort of offset voltage induced by the difference between the current entering the two branches of the open. Okay. So the total offset effects are represented here. So when referred to the input, you can, well, we have basically computed this two quantity here. If you want to move back the offset to the input, you have to divide the quantity times the transfer function. Okay, so but what should be concluded is that indeed R3 can be used to somehow compensate for the effects of IB minus and IB plus. Okay. So the inverting and non-inverting configuration are indeed quite common in analog systems. But in multiple cases, rather than amplifying just one signal, we are facing different signals, okay, differential signals. To amplify differential signals, so the signals applied on two lines, two wires, okay? What we can do is to use the so-called difference amplifier. The difference amplifier works in this way. So the idea is that we can compute the effect of the inputs on the output by applying the superposition principle. So first we plug just input number 1 and we set V2 to 0 and vice versa. Okay, and then we add the two effects. So when V2 is equal to 0, then, and if we can neglect the input current here, then the voltage drop over R3 and R4 is null. Okay, so V1 is processed with a transfer function, which is the one of the inverting configuration, because here it's like having ground voltage. When the input is voltage number 2 and voltage number 1 is grounded, then we have a voltage divider effect between R3 and R4. And then from this point on, the configuration is coincident with the one of the non-inverting amplifier. So suppose that rather than focusing on VI1 and VI2, we change these two variables into a differential effect, so VI1 minus VI2, or vice versa, and the common mode effect. You cannot read it, okay? So VID is VI2 minus VI1. And V common mode is, as usual, VI1 plus VI2 divided by 2. So the average between VI1 and VI2. Suppose also that we select the ratio between resistor number 4 and 3 so that it is equal to the ratio between resistor number 2 and 1. Okay, so in these circumstances, we can compute the input-output relationship as shown here. So basically, we flip the former relations, and we can say that VI1 is common mode minus VID divided by 2. Okay, so by inverting this equation. Okay, so VI1 is equivalent on having V common mode minus VID divided by 2, while VI2 is V common mode plus VID divided by 2. Okay, so we are turning the two independent input sources into a scheme like this, with the common mode applied to this intermediate node and two differential voltages applied here and there. So again, let's get back to the superposition principle. So what happens when we plug VI1 with this expression here? Well, simply we have to multiply this quantity times minus R2 over R1, because this is the effect of the inverting configuration. What happens when VI2 is applied to the scheme? Well, we have to multiply this quantity times the voltage divider effect, so R4 over R3 plus R4, and then we have the effect of the non-inverting configuration, which means 1 plus R2 over R1. Okay, if we plug this result and this one, and we take into account a situation in which the differential voltage is equal to 0, so this term is cancelled, what you get is this expression here. Okay, so if you collect all the signals and if you assume that R4 over R3 is equal to R2 over R1, then the bottom line is that the common mode voltage is equal to 0. Okay. If you repeat the same calculation, but now assuming that the common mode is equal to 0 and VID is different from 0, So calculation number 2 is done by canceling the common mode part. And again, if you assume that R4 over R3 is equal to R2 over R1, well, you get a quite nice simplification. And at the end of the day, you can find that the differential voltage, that is V out over VID, is equal to R2 over R1. So this configuration here, it is very interesting because basically it cancels out all the common mode effects and amplifies just the differential effects. Okay, so with this configuration, difference amplifier, you achieve this goal. However, this nice cancellation of the common mode effects can be compromised if this relationship here is not valid, or if it is valid just to some extent. So let's see what happens when we have a slight variation of one resistor. So the configuration is this one. R1 and R2 in the top branch. And in principle, we should have the same resistors also in the bottom branch. To this guy, we can apply the common mode voltage minus the half of the differential. And to this one, we are applying half of the differential plus the common mode. Now, if all these resistors are perfectly matched, then we have just the differential gain V out over VID, which is R2 over R1, and no common mode gain. So V out over V common mode is equal to 0. This is the ideal situation, okay? But you cannot realize perfectly matched resistors, okay? Nor transistors. So suppose that there is a slight variation of this resistance here. Rather than being rigorously R2, is R2 times 1 minus epsilon. What happens to V out? Well, superposition principle. So V out is equal to common mode minus VID divided by 2 as input of the negative branch. So this means that should be multiplied times minus the resistor here divided by the resistor here. So minus R2, 1 minus epsilon divided by R1. And then we have the effect of the second branch. The effect of the second branch, taking into account that the input is common mode plus the input differential divided by 2. Then we have the partitioning, so R2 over R1 plus R2 time the non-inverting the configuration transfer function. So 1 plus R2 times 1 minus E divided by R1. Okay. So now we can take this formula and decouple the terms which are multiplied by the common mode. So ACM times the common mode, where ACM is the multiplication and the summation of all the factors multiplying this guy. And then we have a differential part which multiplies all the terms with the VID. Okay, so we are decoupling one part from the other. If you do so, you can find that the actual value of AD is equal to this quantity, R2 over R1 times 1 minus R1 plus 2R2 divided by R1 plus R2 times this discrepancy term divided by 2. While the common mode gain is R2 divided by R1 plus R2 times the discrepancy term, okay, epsilon. So you can see that the larger is the discrepancy between the resistor which should be equal, the larger gets the common mode gain. And let me stress the fact that the common gain is an undesired term. Okay, we want this guy to be equal to 0. Okay, because we have many practical situations in which common mode effects are just due to external interferences, and they are not related to physical quantities that we want to process. Okay. We can compute the so-called common mode rejection ratio, pretty much like we did for the differential pair. And in this computation, so differential gain over common mode gain, well, we can take into account that probably epsilon is a relatively small quantity, so this term here can be considered to be more or less equal to 1. But in this case, epsilon is multiplying directly this fixed quantity, so we cannot cancel out epsilon from this expression. So bottom line is that a good approximation of the common mode rejection ratio is R2 over R1 divided by R2 over R1 plus R2 times epsilon. Okay? So it is very important to control the relationship between these resistors. Okay. You can check whether the effect due to the non-idealities of R1 is similar, and indeed you will see that more or less the result is the same. So how can we cope with this problem? Well, one way is to rely on integrated circuit in which the resistor's value is predefined and well trimmed with accurate measurement procedures. Okay, so for example, for this difference amplifier here, we have granted a matching between the resistors in the order of 0.01%. Okay, so a very minimal discrepancy between the two resistors comes to play. Okay. This kind of difference amplifier, by the way, can be also connected in multiple different ways. But achieving such high precision can be complex, and there may be an alternative to that. Especially because even if we buy a circuit like this, we have the problem that maybe the minus R2 over R1 gain that we get in this case is not sufficient. So for example, in this case, in this specific case, this is just 1 or minus 1. Okay, so in some cases we want different gains, but if we want different gains, we have to change the resistances in the loop, which means that, for example, we may need to add an additional resistor here and then connect this resistor to the output. And we have to do the same for the other branch. So by placing another 25 kilo ohm resistor. But if we do so, the guarantee about the matching of the top and bottom branches is lost. Okay, so we have to indeed test the resistor values so that they are very accurate. We must control the contacting in this circuit to achieve a very precise matching between the resistors. When I say that this can be bought in one shot, I mean that all these op-amp plus resistors come in a unique package. Okay, so you buy a discrete component in which the resistors and the op-amp are within the component. Okay, and then you can add additional resistors in the and connect to the output pin of the integrated circuit. Okay. Okay, so how can we cope with the limitation of the difference amplifier? So these guys are relatively inexpensive, but they indeed have a limited gain because typically it's difficult to have a very good matching at different scales. Okay, so we typically select when we buy this component with just slight differences between what we have called R1 and R2. Moreover, using these resistors, as you may remember by from the noise chapter means adding noise sources, because resistors, of course, are affected by thermal noise. And another important issue is related to the fact that the input resistance of this guy is not infinite, because we have indeed these resistances which act as resistances, as input resistances for the sources which are placed, which are attached to this node. Okay. Remember that in typical configuration, it's when we want to amplify voltage signals, we want also very high input impedances in order to minimize the voltage divider effect across the output parasitic resistance of the source. Okay, so we have a source which generates the voltage. We have RS. We want the input resistance of the following amplifier circuit to be as large as possible in order to have a small voltage drop across RS. Okay. To achieve more gain, higher input impedance, and superior common mode rejection ratio, we will exploit a new configuration which is called the instrumentation amplifier. This circuit here is very pervasive in precision measurement task. Okay, so whenever you have a very weak signal to be amplified, okay, and you want to be extremely accurate, so what you do typically is to find a difference configuration, so that rather than measuring one single voltage, you measure a difference between two voltages. And then you use the instrumentation amplifier to have high common mode rejection ratio, high input impedances, and more easier way to tune the gain of the global circuit. Okay, just a quick look at a possible initial approach to realize an instrumentation amplifier. The idea is that since one of the problems is the input impedance, so rather than interfacing the difference amplifier, that is this guy, directly with the source, we interpose two buffers. Okay, so two non-inverting configurations. One dedicated to the negative input and one to the positive one. By doing so, we have two main advantages. First of all, as you may remember, the input impedance of op-amps is typically very large, so we have a nice effect in terms of source load. Second effect is that since we have this non-inverting configuration, which are amplifying configuration, then we have an additional amplification step to be used for the global differential gain setting. So the differential gain in this new configuration is not just limited to the gain of the difference amplifier, which in this case is R4 over R3, but we have this additional term which can be very useful. Okay. However, this topology has also some limitations. One limitation is that the matching issue that we have analyzed in the difference amplifier case, so when we have considered the fact that R4 can be actually R4 minus a given quantity, can be applied also to the initial part. Okay, so if R1 and R2 are not perfectly matched to the R1 that we have here, and R2, then we have an additional common mode effect, which is unwanted. Another issue is related in applications in which we wanted to change the differential gain, we have to change at least 2 resistors in parallel, okay? With again, the same issue related to the fact that we have to control very precisely that the matching is accurate, okay? So this is just an initial idea. The actual implementation of the instrumentation amplifier is shown in the next slide. And the idea basically is to replace this connection here. So resistor number 1 grounded and resistor number 1 grounded as well at node X, with a configuration in which we remove the ground connection and we keep 2 times resistor 1 altogether, okay? There is no time to analyze the benefits of this solution, so we will get back to this issue on Monday. Thank you very much for your attention and see you next week.